Woohoo! Welcome back. Tonight we're going to be working with geometric sequences. Yay! And geometric sequences follow the same pattern as arithmetic sequences, but with multiplication. Woohoo! So, in a geometric sequence, instead of the common difference, there's a common ratio called R. The first term is still referred to as A, and the general form is this. So instead of A plus D, we've got A times R. We still have the n minus 1, but now that is an exponent as opposed to a factor. So let's take a look at an example and see what I'm even talking about. So if you look at 3, 6, 12, 24, etc., and you're saying, well, how do I know it's not arithmetic? The answer is if you look at the terms, you say, okay, to get from 3 to 6, I could add 3. And then to get from 6 to 12, I would add 6. And then to get here, I would add 12. And then I realize, oh, yeah, this is not. So this is not just a single difference that matches every time. So this is not arithmetic. So how do we know it's geometric? Well, the next thing we would try is we'd say, okay, is there a common ratio? 3 to 6 is times 2. 6 to 12 is times 2. 12 to 24, again, times 2. So if there is a common, we call it a ratio, but in this case, we're just multiplying by 2. So we're looking at multiples. Then we know this is geometric. Oops. Sequence. There we go. Started to write a different word there. That's always exciting. Okay, so how do we set up the general form? Well, given that each time we're multiplying by 2, that means R equals 2. And then A, which is just whatever the first term is 3. And then our general form, A sub n, is A times R to the n minus 1, which is 3 times 2 to the n minus 1. That's our common ratio, or that's our general form. Sorry about that. With the common ratio right there. And then it says we should find the first 6 terms, the nth term, here's the nth term. The first 6 terms, 3, 6, 12, 24, and to keep going, multiply by 2, then I get to 48, you got it, and then I'm going to go again, multiply by 2, and I get to 96. So here are the first 6 terms. Here's the general term. And what's the 100th term? A sub 100 is going to be 3 times 2 to the 99th power. Now, this is sometimes going to be very difficult. So let's take a look. I'm not sure. To be honest, I haven't double checked on this calculator. We may not be able to calculate that high. So let's try it. 2 raised to the 99th power. And as you can see, it's having to write it in scientific notation. So I'll go ahead and multiply by 3. Oops, sorry about that. And so we get, in scientific notation, 1.90147 59 whatever else times 10 to the 30th power. So that is a pretty big number because that means that we've got to move this decimal place over 30 spaces. So it would be this whole number 1, 2, 3, 4, 5, 6, 7 plus another 23 zeros. So this is a very, very large number. And as you might guess, geometric sequences, if the common ratio is something like multiplied by 2, then the numbers are going to get really big really fast. Okay, let's try another one. Yay! Now, this one is interesting because if you notice, it's something called alternating because we've got a positive, then a negative, then a positive, then a negative. You can't get that in an arithmetic sequence because with an arithmetic sequence, you're either always adding or always subtracting. And so you won't get that flip-flopping. But if we take a look here, this is multiplied by -5, and then this is multiplied by -5, right? 2 times -5 is -10. -10 times -5 is 50. 50 times -5 is -250. So our first term is A, which is 2. Our common ratio is -5. And so our general form is going to be A times r to the n minus 1. So that's 2 times -5 to the n minus 1. And it is perfectly fine to have a negative common ratio. So let's go ahead and complete this to -10, 50, -250. Okay, to get the next two terms, because the instruction said to go to 6 terms, -250 times -5, and that's 1250. And then times -5, we get to -6250. And because we're multiplying by that common ratio, which is negative, we're going to end up flip-flopping, positive, negative, throughout the whole sequence. Okay, so those are the first 6 terms, and then we need to do the 100th term. Now, I'm pretty sure this is going to be pretty big, but let's give it a try. It's going to be 2 times -5 to the 100 minus 1. So that's going to be 2 times -5 to the 99th. So let's see if I can get away with this. I've got -5. I'm going to raise it to the 99th. Let's see if that confuses. It didn't confuse the computer in the calculator, but we're getting pretty big. And then I multiply by 2. And so this is going to be the 100th term, right? Because the second term, the 4th term, the 6th term are all negative. The 100th term, also negative. And that's going to be -3.155443621 times 10 to the 69th. So this is even bigger because our common ratio, even though it's negative, it's large in absolute value. So you can imagine this has just got tons and tons of zeros. This is a massive number. Okay, so let's go for one more puzzle. And we did this with arithmetic sequences, and I want to do this with geometric sequences. And so this is the puzzle that we're going to get. And it says we're not given anything about the geometric sequence except that the third term is 63/4, and the 6th term is 1701/32. Okay, so then what? Well, we know that in general, a sub n is equal to a times r to the n minus 1. So a sub 3 should be a times the common ratio to the 3 minus 1. So that's a times r squared. The 6th term is going to be a times r to the 6 minus 1. So that's a times r to the 5th. And so I know that a r squared equals 63. Oops. My hand loves writing whatever it feels like. 63/4. And we know that the 6th term, ar to the 5th, is 1701/32. Now, With an arithmetic sequence, we set up a system of equations to solve this. We had a very similar problem, and we had A and D, and we solved it in the last section. Now for this one, subtracting these won't necessarily help us out. But I will point out that if I take AR to the fifth, and I look at the ratio between that and AR squared, the A's cancel, right? And the R's kind of cancel, and we end up with R cubed on top. 2 of the R's cancel with 5 of the R's and leave 3 of the R's. So that R cubed would be equal to, and I know this is everyone's favorite thing, but we're going to go ahead and take the ratio of 2 fractions. I know, not really anyone's favorite thing, but let's give it a try. So I've got 1701 over 32, right? That's AR to the fifth is this one right there, all over AR squared, which is 63 over 4. The trick is to remember that when you have fractions like this, you use division. So let's put it back in division in that symbolism. 1701 over 32 divided by 63 over 4. So that's going to be 1701 over 32 times 4 over 63. And remember, this is going to be R cubed. Okay, so now let's see what we can do. I know that 4 goes into 32 and leaves 8. I do not know about 63 and 1701, so let's go ahead and see what we can do. 1701 divided by 63, does it go in? Yes, it does. And we end up with 27. So R cubed equals 27 over 8. Okay. Which is, can we put that in cube form? So if it's 27 over 8, that's 3 cubed over 2 cubed, right? Because 3 cubed is 27, 8 is 2 cubed. So if that's R cubed, then R equals 3 halves. Does that make sense? Okay, so then, oh no, do I not have any? Do I have one piece of paper? Thank goodness, one piece of paper left. So if we know that R equals 3 halves, we need to find A, right? So we can come back to this fact. We know that AR squared equals 63 over 4. So this is A times 3 halves squared equals 63 over 4. So we're just slowly chipping away at this puzzle. 3 halves the quantity squared is going to give me 9/4. And that's going to give me 63/4. And now a lot of people would say, oh, I can see what the answer is. And if you're not sure, then what you can do, let me give some room, is I'm going to multiply both sides by 4/9. And the reason for that is then I can cancel, and I end up with just A on the left. And then over here, the 4's cancel. 9 goes into 63 7 times, so A equals 7. So our general form is going to be 7 times 3 halves to the n minus 1. And this is our A, and this is our R. If we go back to the problem, it says find the 5th term. So A sub 5 is 7 times 3 halves to the 5 minus 1. So that's going to be 7 times 3 halves to the 4th. Oops, sorry, let me scooch it up so you can see it. 7 times 3 halves to the 4th, which is equal to 7 times 3 to the 4th all over 2 to the 4th, which is 7 times 3 to the 4th is 81. 2 to the 4th is 16. 7 times 81 is 567, I believe, all over 16. Oh my goodness, that was a lot of work. So the notes will be up in Canvas, so make sure you check the notes, because this problem, a lot longer than the problem that we did with arithmetic sequences, but we can still do it, and we can still solve this puzzle. So, woohoo! And so I'm going to end this video now. We're going to go on. In the next video, we're going to do, just like we did with arithmetic sequences, we'll look at partial sums, and then we're going to move on to something called infinite series, which is ultimately the goal of this chapter. So, woohoo, go get yourself a nice snack and something to drink, and maybe rest your eyes a little bit, celebrate, dance around, take a nap, all the things that, you know, make life awesome. And then come on back and we'll do some more math, which also makes life awesome. And I'll see you there. And then, woohoo, math on.